it's more dur.
Okay, sorry about that.
Don't worry.
And he's going to talk about non-local birth-death processes. So your birth is 1 minute after 9, and the death is another 30 minutes, including questions. So please, Giacomo.
Okay, so let me just start from the title of the talk. First of all, let me just thank the organizers, the first thing. But then let me start from the title of the talk. So I just referring to the processes I'm trying to introduce here as non-local birth-death processes. But here I should add 2 words: time before non-local, and then solvable after non-local, because I'm just focusing on a class of certain kind of birth-death processes that are not really birth-death processes. We will see we will see in the next slides that we are focusing on the case in which we are talking about semi-Markov processes, and we carry on some time non-locality, and solvable because I'm focusing on the case in which we can just say more or less everything from a spectral point of view. And let me just go ahead and you'll see what I mean. So first of all, let us recall what is a birth-death process. So in this talk, I fix a probability space, and I always assume everything is supported on here. And we consider as state space for our processes a set of the form 0, 1, etc. And we suppose it is finite, or it is actually the whole set of natural numbers, including 0. And the birth-death process is a continuous time Markov chain in which states can change only by stepping forward on 1 step or backward on 1 step. And at 0, they can only move forward. Actually, there is also a definition of birth-death processes that can have killing mechanism that actually we can call it extinction. That is to say, from 0, I can just move backward to -1 and then stop here. But I'm not focusing on this case. I'm just considering the case in which from 0, I can only move forward. And just from the transition graph, we can see that the generator of a birth-death process is a possibly infinite tridiagonal matrix. We call the Bn the birth rates and the Dn the death rates. So as I said, the generator can be seen as a tridiagonal matrix, possibly infinite, depending on the fact that the state space is finite or not. And we can define, starting from this tridiagonal matrix, a sequence of polynomials that are associated to the generator. Such sequence of polynomials is always orthogonal with respect to a positive regular measure. And this is a theorem by Favart. And the L2 norm with respect to this positive regular measure can be determined by starting from the birth and the death rates. And here we have a closed formula for it. And actually, such a measure is called a solution of the Stiltis moment problem. That's because this condition here are actually conditioned on the moments of this positive regular measure. And in these settings, we have 3 equivalent formulations of the existence of uniqueness of the solution of the Stiltis moment problem. First of all, there exists a unique matrix that is solution of both this system of ODEs, starting from the identity matrix, and that is bounded at each time for some constant that is greater than 1 or 1, greater or equal than 1. And if this is true, then the solution to this problem is unique and vice versa. And moreover, there is a third statement that is equivalent to these two, that is the fact that this series diverges. And this condition here is quite an interesting condition because it actually gives us some information about the birth-death process itself. So when one of these 3 conditions hold, then all the entries of the matrix are non-negative. They sum up to 1, And the following integral representation holds. So we actually have a spectral representation of the solution of these two system of ODEs. And for this reason, we just refer to the solution of the Stiltis moment problem as the spectral measure of the birthday process. So why did I say that the condition about the series is actually a condition on the birthday process? That's because we can split into part the series we have in the third statement, and if the first part converges while the second part diverges, the process is ergodic. And actually, this is a characterization of ergodic birthday processes that are not killed at 0. And in such case, we can actually reconstruct the stationary distribution from the L2 norms of the orthogonal polynomials we defined before. Let me just stress out an important thing. The spectral measure is not necessarily discrete. And to recover the spectral measure, we can actually argue by using the Laplace transform of the solution of the two equations we said before and the polynomials that can be actually reconstructed from the generator to actually reconstruct the Stiltis transform of the spectral measure, and then we can just use Stiltis inversion. So now that we have set the basics of birthday processes, let me just change a bit the notation in what we are working with. So by now, the birth rate and the death rates will be denoted as functions of a natural number. This matrix will be denoted as a function of 3 variables. The time and 2 natural numbers is just the probability of jumping from J to I. The stationary measure, Mn, in the case our birthday process is ergodic, will be identified as a measure on the natural number, and we can just define a measure on the natural number by just giving the value Mn to a singleton set. And we can introduce some operators that will play the role in a certain sense of the derivative in these settings, that are the forward and backward difference operators. And after defining these operators, I can also define this other operator here that is the second order central difference, that actually is more or less a Laplacian. The idea is that we are talking about a sort of second order derivative. It's just like the Laplacian. And if we introduce these operators, we can rewrite the generator in this form. That actually recalls, in some sense, the generator of a diffusion process. We have the derivative, and we have the Laplacian here. D and B are actually functions. And G is an operator acting on a certain space of functions from natural numbers to real numbers. That is just the space of infinitesimal sequences. And the relation that we wrote in this form before can be rewritten as the action of a certain operator L that we will call forward operator on the function P. And the forward operator, if we try to rewrite this relation, is identified by this formula here. Actually, the forward operator plays the role of the Fokker-Planck operator. When the generator gives us the backward Kolmogorov equation, the forward operator gives us the forward Kolmogorov equation, or the Fokker-Planck equation, of, as we want to call it. And there is a link between the eigenvalues and eigenfunctions of the backward and the forward operator, as we will see in the next slides. Precisely, as I said, I'm interested in some specific class of birth-death processes, classes for which we can say a lot of analytic properties. So I call them solvable. They are not all the exactly solvable birth-death processes, but it's the class I'm focusing on. I'm asking for them to be ergodic and irreducible, and asking for the generator to be of purely discrete spectrum, and I'm asking for all the eigenvalues to be 0 the first one, and negative all the other. D should be a polynomial of degree at most 2. B minus D should be a polynomial of degree at most 1. And the stationary measure that exists, since I'm asking for the Burdett process to be ergodic, should solve this equation that I call the discrete Pearson equation. Why I call it, the motivation for this name will be clear actually in the next talk by Nikolai. And the eigenfunctions of G are m-orthogonal polynomials. What we are actually saying is that the discrete Pearson equation guarantees that the stationary measure is at the same time the spectral measure of the process. So we're talking about a situation in which the spectral measure and the stationary measure coincide. But actually, we're talking about not so many Burdett processes, because any solvable Burdett process is or a finite state space, or is it an immigration Burdett process, or is it a linear Burdett process. Just to see what we are talking about, we cover all the finite difference approximations of the generator of a first-class Pearson diffusion. Actually, it does not seem, if we just consider steps of amplitude 1, but with the proper spatial and time scaling, we actually obtain all the finite difference approximations. And any distribution belonging to the Katz family is actually a stationary distribution for some process of this kind. Vice versa, any stationary distribution of a process of this kind belongs to the odd family of distributions. And then we have a closed formula for the eigenvalues. We can also define another function that at the same time defines a measure on the state space that it will be called the dual measure, and the orthogonal polynomials with respect to this measure are called the dual polynomials of the polynomials P that we are defining before. Oh, actually, I forgot to say, here I'm using P for the polynomial since I actually resetted all the notation just to not use too much notation. Okay, just to say P here is a polynomial. Now we are talking about the orthogonal polynomial of the Burdett process. And we denote by Qn the normalized orthogonal polynomial, so that the L2 norm of Qn is 1, just this. So let me just consider the two important cases. This is the immigration Burdett process and the linear Burdett process. The immigration Burdett process, we will call it Charlier process for a reason that will be clear now. So the immigration Burdett process admits constant Burdett rate, but linear Burdett rate. Sorry, here, yeah, it should be, it is true. Okay, its spectral measure, that is actually the invariant measure, as I said before, is the Poisson measure. The eigenvalues are of this form. The eigenfunctions are the Charlier polynomials that are defined as a Scheffer system in this form. The dual measure is actually, again, a Poisson measure up to a constant. So what happens is that the orthogonal polynomials are actually, the dual orthogonal polynomials are actually the same as the orthogonal polynomials. And we have actually this self-duality property, that is to say, for natural values of x, that are the ones we are interested in actually, we can exchange in a certain sense the degree of the polynomial with the argument. And this will be actually crucial in the main results. And something similar happens for the linear Burdett process that we call here Mexner process, since we are considering a linear Burdett, linear Burdett rate this time, and the spectral measure is the Pascal measure with eigenvalues that are still linear functions of n, but this time they admit d minus b as coefficient. And the eigenfunctions this time are Mexner polynomials. They do not form a Scheffer system unless we multiply it by a Poinchammer symbol that I wrote here as the quotient of two gamma functions. The dual measure is still a Pascal measure up to Pascal or negative binomial. Let me just to give some names, up to a constant. So what happens here is again that we can exchange the degree of the polynomial with the argument when we are talking about natural numbers. And again, this property will be quite important. And we can rewrite the spectral decomposition in this form. So as a series, the forward operator admits as eigenfunctions the product of the normalized polynomials with the spectral measure, and the eigenvalues are the same of the generator. And each time I'm studying the backward Kolmogorov equation, then I can rewrite the solution as a sort of Fourier series, and the same I can do with the forward Kolmogorov equation, except for the fact that you have to start in the backward case with L2 initial data, while for the forward case I have to ask that the ratio between the initial data and the spectral measure is L2. So let me just go straight ahead on the fractional calculus case. So I think we have already seen such definitions in the previous talks. We say that the function is a Pearson function if it admits this kind of representation. Actually, this is another kind of, if we can say that it is a Pearson function if it is the Laplace transform subordinator and so on, but Laplace exponent, sorry. But let me just focus on this representation, that is the Levi-Khinchin representation of a Pearson function. A and B are two constants, and E is a unique Levi measure satisfying this additional integrability property. A Pearson function is said to be complete if the Levi measure admits a density that is a complete monotone function. And in our case, let us suppose that the killing coefficient A and the drift coefficient B are 0, the Levi measure is infinite, and we call ni bar the tail of the Levi measure. Now, let me recall rapidly what is the definition of subordinator. I think that is the sixth time we've seen it in this workshop. And for any Pearson function, there exists a subordinator that admits it as Laplace exponent and vice versa. We can define the inverse of subordinator as, well, right continuous inverse. And under our hypothesis, we know that sigma, the subordinator, is a pure jump process, is strictly increasing while the inverse is continuous. And the inverse is, for any fixed time, the inverse is an absolutely continuous random variable, so it admits density. And we can actually define, starting from this representation of Pearson function, some form of Caputo type derivatives by considering the convolution of the L1 derivative of a function of an absolutely continuous function with values on a bank space and the tail of the Levi measure, supposing this convolution exists as a Buckner integral. But if we ask f to be absolutely continuous, this convolution always exists as a Buckner integral. And we have some clear examples, such as the Caputo fractional derivative. We consider phi to be the power function, but we also get the temperate fractional derivatives if we consider phi to be something like this, and the Caputo-Fabrizio derivatives that are non-singular derivatives if we consider our Pearson function to be like this. And we can also define some Riemann-Liouville type structure for this non-local derivative. And if we do this for any absolutely continuous function, we can actually recognize that this Caputo type non-local derivative is actually the Riemann-Liouville non-local derivative of f minus the initial data. And this let us define some Kara-Theodori solutions for non-local ODEs. Well, the non-local derivative actually admits some exponential-like functions that are the moment-generating functions of the inverse subordinators. And actually, we can say that such quantity is the unique solution, unique strong solution of this non-local Cauchy problem. And it has been proved in several situations, in several works, and so on. And there is a well-known case, if we consider phi to be a power function, that this quantity is a Mittag-Leffler function evaluated in minus lambda t at alpha, when we consider lambda to be negative. Also, let us recall that so when I consider lambda to be negative and I send lambda to minus infinity, this function decreases, and we can still control it if we multiply by modulus of lambda. Here I consider just minus lambda and lambda positive to just rewrite it in a compact way. And let us also recall what is a semi-Markov process. A semi-Markov process is a process that exhibits the strong Markov property with respect to the stopping time that takes value in this set that is actually the set in which the process changes its value. There is a link between Markov additive processes and semi-Markov processes, but since we are short on time, let me just skip this. Maybe if there are some questions about this kind of construction, I'll just go back. So let me just move on the interesting part. So let us define this kind of spectral series. Here, in place of the exponential, so let me just go back for a second. Just I want to highlight what is the, here for the transition probability function, we have this exponential, this spectral representation, that if this function here is the solution of a classical ODE, system of ODE. Here we have the exponential function, that is the eigenfunction of the derivative. So what we could ask is whether we can just replace the exponential function with the eigenfunction of a Caputo-type derivative and obtain something that still makes sense and admits a clear stochastic representation. So I just go, oh, actually I can click here directly. Sorry. And that's exactly what we are doing here. We are substituting the exponential with this function here. There is a generalized Mittag-Leffler function if we want to use the words adopted by Kolokostov previously in some of the talks we made in these weeks. And actually we're asking if this series is absolutely convergent. And it is, and also uniformly with respect to t. And the trick is that we can exchange, upon rewriting it in terms of orthogonal polynomials, the degree with the argument in this case, so that we are actually studying a sum in which if I start after the last, here we have some fixed degree, so I can just start the sum, I can just study the sum starting after all the roots of these polynomials that are fixed. Since I fixed the degrees, actually I'm not fixing the arguments. If I use the self-duality property, I'm fixing the degrees. So if I study the series starting after these roots, everything reduces to just studying what's happening in terms of the orthogonality relation of these polynomials. And then this quantity is actually between 0 and 1. So if I want to study some non-local Cauchy problems in terms of orthogonal polynomials, I just need to determine whether some particular series converge or not, and in which sense they converge. And here we have one that will play a major role, because we will show that this function here is actually the fundamental solution of a system of infinite ODEs, non-local ODEs. So let us move on some additional series we have to study to ensure the convergence of the involved quantities in the problem that we are going to introduce. And actually, I can just consider an L2 sequence and subdivide it, decompose it as a sort of Fourier series in terms of the orthogonal polynomials. And then what I obtain is that for any x in E, I have this inequality. And this inequality just guarantees that this series normally converges. And also this series normally converges starting from any point that is far away from 0. And this is done by means of just the Cauchy-Schwarz inequality in there. And then after we prove this, we can actually prove this other two with the same trick as before. So what we want to focus on are these two problems that are actually a sort of backward Kolmogorov equation in terms of a non-local derivative here in time, and a forward Kolmogorov equation in terms of a non-local derivative here in time. Here we have the generator and the forward operator of the birthday process we are considering from the start. And we say that a function is a strong solution of this problem if it is continuous as a function from C0 to the space of L2 sequences with respect to the spectral measure, if the non-local derivative exists in the sense of a Bochner integral, and we can actually recognize it as the limit in the L2 norm, and the equation holds pointwise. Moreover, we are asking also for the non-local derivative to be continuous as a function between R0 and the sequences and the L2 sequences, and the same definition are valid for F. So what we obtain is that this problem, if we start from an L2 initial data, admits a unique solution that can be rewritten in this form. This is actually the spectral decomposition of the backward Kolmogorov equation in the classical case, except that we are considering here the eigenvalue, the eigenfunction of the non-local derivative. So the idea of the proof is quite simple. Just you have to ensure that you can exchange the non-local derivative with the series and the generator with the series. Just this, and the same holds for the forward operator. So let me just go straight on the last thing I want to say, and then I stop. That is to say, well, actually, here we have some representation in terms of this function here. That is, as I said, will play the role of the fundamental solution. And this fundamental solution is actually the transition probability function of a certain process that is obtained by using the inverse of a subordinator whose Laplace exponent is the Bernstein function as a clock for our birthday process. And then this I can call a time non-local solvable birthday process, and it's actually a semi-Markov process. So it is not true that the equation does characterize this process, but it is true that if I start from the process, I can characterize the solution of the equations. Since what I get is that the solution of the backward equation are conditional expectation of the initial data evaluated on the process, and if I start from a probability distribution, the solution of the forward equation are the probability that I can find the process at position X if the initial law of the process is actually the initial data. And I think I can stop here because I don't think I have time for some other details. Let me just stress that despite the process can be the parent process can be stationary, the new process is not second order stationary, despite it is first order stationary. So one has to pay attention when covariance is studied, because the formula for the covariance is not so clear, and it does not depend on the time interval that is passing by. So let me just stop here, since I think that the important things are said, and thank you for the attention. And I can hear you if you're asking me something. No, I can't hear you at all. Well, I think you in the room should unmute, because you're muted up to now, and
Maybe.
Okay, now can you hear?
Okay, maybe send him by chat. I'm sorry. And you want to say something? Yeah, can you hear him? I don't think he can hear you.
Well, I cannot hear anyone that is talking without a microphone, it seems.
Okay.
Hi, Giacomo. Enrico here. I would like to ask you a question on possible generalization. So what's the difficulty of doing the time change with a generic counting process, which is maybe not in the class that you have discussed?
So let me just stress that the class I discussed is actually good class to start, just because we have this self-duality property. So I think that the possible difficulty in a generalization, now let me just stress that for any birthday process, one can provide a spectral decomposition. That's what Carly and McGregor proved. But actually, the problem is that you need to evaluate, you need to prove that series of this form are convergent. And here you are studying the dependence of the polynomial with respect to the degree for a fixed argument. And here you have something of which you don't know exactly what is the, you don't know exactly what is the asymptotic behavior with respect to the eigenvalue. It's just this the problem, because the trick of using self-duality in this class is that you can exchange n with x, control this because it is bounded, and then say, okay, then I work with orthogonal polynomial. I can work with orthogonal polynomials. I know how to work with orthogonal polynomials since I have also the right weight against them. I think that a possible generalization can be obtained by using dual polynomials instead of using self-duality, but I'm not sure 100 if it turns well. I think the main difficulty could be this one. Also, the fact that this is a series here, but in the general setting, it could be an integral. Let me just stress out this. It could be an integral. So I think that's all. I think for a counting process, you can actually work it out in some way. But yeah, I think that the real problem is that you have to prove that this kind of series are convergent, and you need some properties of the polynomials. That's all.